Okay, so first let's start just to make sure we understand our definitions. Let's say we have a set A and we have a set B. And in set A, I have some things. I will make them numbers. And in set B, I also have some things, and I will make them numbers as well. And a function from A to B is a set of ordered pairs where the first element comes from set A and the second element comes from set B. And so this is a function from A to B. Write it like that. You'll notice that I did not actually use all of the elements of B, and that's okay. The things that I used are what are called the image of F. So I can also define F to go from a subset of A to B. Now, just because this is the way you're doing it in class, we'll call a subset of A X and a subset of B Y, and these are capital letters, and he's putting little lines on them. So that would be a subset of A. So X is contained in or equal to A, and Y is contained in or equal to B. That's just the way they're done here. We could call them whatever we want. Now, if I'm looking at my entire set here, then we also have this definition where we talk about F of a subset. Now here, my subset will be my entire set. So F of capital A, you'll notice, does not equal B. F of capital A equals a set 0, -1, and 3. This is also called the image of A. It's everything that's in there. Now, one thing, going back to our definition of the function, you may notice that this first element could never repeat. That's important with a function, that I cannot have both 1, 0 and 1, 3. If 1 shows up again somewhere as a first element, then it had better have 0 as the second part of that ordered pair. Now, I'll define X to be a subset of A, and I'll define X to be the subset 3, 5. Now, F of X, now let's look and see what the definition is that he gave you, so make sure we're defining it the same way. So I'm going to copy these things right here. Let me move that. Okay, so he wanted to make sure that you understood that F from A to B means that if you have X, we're going to say that's a subset of A, and Y is a subset of B. So F of X, what we need to get from this needs to be some subset of B. So we'll just call that Y for right now, and let's see what that is. F of X is going to be, we look at our function list here, it will be F of 3 is -1, and F of 5 is 0. So if X is this, then F of X is that. Okay, now that's what this line is saying right here. F of X is the set of F of X's such that X belongs to X. So if this is F, our entire set of F of X's, if this is our entire listing of X, our entire set of F of X's are 0, -1, and 3. You'll notice that's the same as what I wrote up here. So this is our entire set of F of X's. Now, F of capital X includes all of the things in here such that X belongs to capital X. So in other words, it includes, so F of capital X has to include F of 3 and F of 5, or in other words, what we had here, -1, 0. Okay, so, and just to make sure that you're clear, F of X is a subset of b. Right there. F of x is a subset of b, and x is a subset of a. So that's really important to keep in mind, that whatever your thing you're taking the function of, I have f of a, that by definition means that little a has to be in a, but f of a has to be in b. Okay, now our functions they don't have to be finite the way we had here. We can also have a function that's more like a function that function that's more like what you're familiar with. Let's see, can I actually move this? Yes. Okay, so a function that's more like a function that you're familiar with. So I could have my set A be the real, that's a nice line, the real number line, and I could have my set B also be the real number line. And I can define a function from A to B as being, let's do the absolute value function. So that will be my function. And so I can't list out all my points because this is an infinite number of points, but for example, I would have the point -1, 1. I would have the point -1/2, 1/2. I would have the point 1/2, 1/2. I'd have the point 1, 1. I'd have the point 0, 0. All of these things would be in my f of x. And so my x's include all of the reals. My f of x's don't actually include all of the reals because I can't ever get to any of these over here. So my f of a, if I were to say f of the entire real line, is going to be a subset over here. It's just going to be the non-negative numbers. So let's take a look at an example. If I take x being a subset of a, and I'm going to let x be the interval, I'll have a closed interval, the interval from 0 to 1. Okay, so these values are in here. Then f of x is going to be a subset of b, and it's going to include all elements of b. Now it turns out b here are also the real numbers, but it's going to include all elements of b that are of the form f of x. So it's the set of all f of x where x is an element of capital X. So that means if I take the absolute value of all of the numbers in here, those are my f of x's, absolute value of all my numbers in here, what do I get? Well, I get this same thing. Okay, now if I make a new subset, and I have x2, and I'm going to make x2 the subset from -0 to 1, -0 to 0, then this should have been f of capital X right there, because I was taking f of the entire subset. F of capital X2 is going to equal the set of all f of x, where x is an element of x2. Now notice this set has to be part of B, and this set is also going to equal the interval from 0 to 1, because I take any point in here and I take its absolute value and I get that. Okay, well now let's talk about what f inverse means. So I'm going to go back and put a new function on here, just because I don't know what my old one was. Here's A, 1, 2, 3, 4, 5. Here's B, 0, -1, 2, 3, 4. And I'll have my function be 1, 0, 2, 0, 3, 2, 4, 3, and 5, 2. Okay, so now I'm going to let x be a subset of A, and I'm going to let x equal 1, 2, 3. Okay, so now f of x, just like what we did before, is going to equal 0 from there, and 0 again, I don't have to write it, and 2. Okay, x is a subset of A, f of x is a subset of B. Okay, that's good. Alright, now This time I'm going to start with a set in B, so I'm going to call it Y. Okay, Y contained in B, and I'll have the set 3 and 2. Now, I have to be careful if I'm going to be doing an inverse function that I pick things in B that actually have I can take an inverse function of them. Okay, so here's Y element B. Now let's look at what this definition here says. It says F inverse of Y equals the set of all X that belong to X, capital X, such that F of X is in Y. Okay, now, really important to realize that F inverse of Y, this is important, F inverse of Y is a subset of A. So F of Y is a subset of B. I'm sorry, F of X. There is no such thing as F of Y. You can't say F of Y if we're defining Y to be points over here. F of X is a subset of B. F inverse of Y is a subset of A. So F inverse of Y is made up of X values. F of X is made up of Y values. Okay, so F inverse of Y are going to be all X's and X's such that F of X is an element of Y. So let's look here at what we defined Y to be. Okay, Y is 3. So I need to go back and look at my X's and see which X's, if I take F of them, give me 3. Okay, well, okay, if I take F of 4, I get 3. That's the only one. Okay, now let's do 2. Which X's, if I take F of them, give me 2? That would be 3 and 5. So F inverse of Y is the set 4, 3, and 5. And 4, 3, and 5, those values have to come from A, and notice that 5, for instance, isn't even an element of B. Now, we can also talk about the inverses with a function like what I had before with our absolute value function. If I have my set Y, now that's going to be in my image. My set Y is the set of -3, so I'm just going to have real just points here. No, I can't have those. Those don't work. My set Y is going to be 2, 0, and 4. Then F inverse of Y, I need to think about all X's that if I take the function of them, give me these. So it's my absolute value function. So absolute value of 2 equals 2, absolute value of -2 equals 2, absolute value of 0 equals 0, and there's not a -0. Absolute value of 4 equals 4, and absolute value of -4 equals 4. Okay, so now let's go ahead and take a look at that proof. I'll put this back up here. Okay, and so what we want to show is that F inverse of Y1 intersect Y2 equals F inverse of Y intersect F inverse of Y1 intersect F inverse of Y2. Okay, so we want to show containment in both directions. Now let's keep in mind what we had like from before, that this is a set in A, a subset of A. This is in A. This is in A. But this is in B. That's in B. And that's in B. So we have a function that goes from set A to set B. Inside B, I have a Y1 and I have a Y2. And over here, I have something, and this, what's in here, if I take F of everything in here, I get Y1. So this is F inverse of Y1. It consists of all x's that if I take f of them, I get something in here. There's nothing in here that does not, if I take f of it, is not in y1. Okay, I also will have something else here. Let me use a different color. Okay, this will be f inverse of y2. Now, if I take f of everything in here, then I will get y2 over here. So what my goal is to show that this right here corresponds to this right here. That, because these, this is an A and this is an A. So this is f inverse of y1, this is f inverse of y2. And so this part right here, right there, that's f1, f inverse y1 intersect f inverse y2. This is in B, and that brown part right there is y1 intersect y2. So I want to show that if I take f of everything in here, I get exactly everything in here. Meaning I get, if it's in here, there's some x in here that maps to it, and if it's not in there, then it's not in there. Okay, so let's do this in this direction first. I'm going to let x be an element of f inverse of y1 intersect y2. I'm going to stop drawing the little lines. Okay, so I'm going to let x be over here. Then I'm going to show that that means that x is also over here. Now it's okay to call it x because this is in A. So x is in A, so x is something over here. X is an element of A. Okay, so by the definition of inverse, okay, so this is by the definition of inverse, if this set, so f inverse y1 intersect y2 is the set of all x element of capital X such that f of x is an element of y1 intersect y2. Okay, that's the definition right there. Okay, so but what he wanted you to use is, rather than, so that you don't, this is a true statement, but let's not write it yet. We're going to use instead the definition of f of x, what f of x means. So this is what you said in your first email, that if x is an element of f inverse of y1 intersect y2, then that means that f of x is an element of y1 intersect y2. Now let's see why that is the case. If this set contains all of the x in X such that f of x is an element of y1 intersect y2, then if I'm saying x is in that set, so x is in that set, and this is our definition of it, then f of x has to be in this set. That's directly from here. So x being an element of f inverse means that f of x has to be in that set right here. So now notice this is an f of x. F of x is an element of y, which is good because here we're saying it's an element of y1 intersect y2. Just make sure I'm clear on that. So we've got, we let x be an element of this set. This set is a set in A. We don't know yet that it equals this, but it's over here. It is the set of, we do know we're starting here, we're saying we have y1 intersect y2, that's this part. F inverse of y1 intersect y2 are all of the x's over here, wherever they may be, that if I take f of them, I end up right in here. So x, if I look at what this set is, right here, this set is the set of everything over here that when I map it, it ends up in here. So that means if x is in this set, if I take f of x, it has to end up in this set. So that's what this line right here says. Okay, well now just by the definition of intersection, so this is definition of intersection, f of x has to be an element of y1, and f of x has to be an element of y2. Okay, now, by the definition of inverse, I can let f inverse of y1 equals the set of all x, element of x, capital X, such that f of little x is an element of y1, and f inverse of y2 is the set of all x, element x, such that f of x is an element of y2. Now these are different x's, this is just defining what the set is. Okay, so let's take a look at this really clearly and see if f of x is an element of y1, here we go, f of x is an element of y1, then x has to be in this set. Because what is this set? This set is the set of all x's, so that f of x is in y1. Well, our particular x, the one we chose right here, is in y1. So x from this one, we know x has to be an element of f inverse of y1. Now let's look at this. If this f inverse of y2 is the set of all x and x such that f of x is an element of y2. Okay, well let's look at our particular x. Our particular x, f of x, is in y2. Okay, now this set is the set of all x's such that f of x is in y2. Okay, so our x has to be an f inverse of y2. Alright, well now we're done because x is in f inverse of y1, x is also an f inverse of y2. So from that, by definition of intersection, x is an element of f inverse x1, y1 intersect f inverse of y2, which now we have shown containment in this direction. So we can say f inverse of y1 intersect y2 is contained in or equal to f inverse of y1 intersect f inverse of y2. Okay, so now let's look at the other direction. If I have time, if I don't finish, I'm just going to have to stop because I have someone coming. Alright, so now we want to show I don't know what I'm doing wrong. Okay, we'll just have it a little quicker. Alright. Okay, my next person is here. So I'm going to have to stop right here, but I hope that what I did works. I'll go real quick before she comes in. So we'll start by saying x is an element of f inverse y1 intersect f inverse y2. Okay, so this implies if it's an element of the intersection. Okay, well first, this is now using our definition of inverse, what this means. This means f of x is an element of y1 and f of x is an element of y2. That comes from our definition of inverse, because if x, this, okay, so f of x Okay, F inverse of y is the set of all x's such that f of x. Okay, let me do a step before this. The step before this would be that x is an element of this and x is an element of that. So we have that. So let's just look at one of those. So if I have x is an element of f inverse of y, 1. Okay, what does y inverse of 1 mean? F inverse of y1 means that this is the set of all x's, so it's the set of all x's such that f of x is an element of y1. Okay, so if f of x is an element of y1, well, that's what we have right here. Oh no, that's what I'm trying to show. Hold on. X is an element of f inverse of y1. So x has to be in this set. So that means that f of x is an element of y1. Okay, I know that's not being clear. Okay, so we go back. X is an element of f inverse of y1. We have that right here. What is f inverse of y1? It's the set of all x's such that f of x is an element of y1. So if x is in this set, by definition, by the definition of inverse, if x is in this set, so by definition of inverse, f of x has to be in y1. Similarly, f of x has to be in y2. So if f of x is in y1 and y2, then we know f of x is an element of y1 intersect y2. Come on in and just pretend like you don't see that I'm talking to myself.
Okay.
Okay, and so then again, by the definition of inverse, if we have that f of x is an element of y1 intersect y2, then if we look at our definition of inverse, our inverse would say that f inverse of y1 intersect y2 is the set of all x such that f of x is in y1 intersect y2, and I have to quit now. And shift.